today's lecture is about one particular theorem, and it is on dimensions. Because dimension is a crucial issue. It is a very important geometrical issue. Because without understanding that, a lot of understanding of linear algebra remains, uh, half baked. So we are calling this chapter of lecture, I have written chapter then put lecture, as the rank-nullity theorem. Rank is also a special name given to the dimension of a special set. Nullity is also a special name given to the dimension of a special set. So what happens if we add these two special dimensions? What would happen? So rank is the dimension of a subspace of some set. Nullity is the dimension of a subspace of some vector space. And if you add them, what will you get? That's the question. So we will initially start by looking at matrices, because matrices are the most visible linear map that we will deal with after this. We will not come back to special maps, special linear maps which are not matrices and go in infinite dimensions, nothing like that. So as a result, we will just focus largely on matrices. But here at the end of this part of this discussion, we will have to, in order to answer a question about a matrix as an operator, linear operator, we have to resort to the study of the rank-nullity theorem in terms of the general linear operator between two finite dimensional spaces. Because matrices would operate only on spaces like only on Rn to Rm, right? But there can be spaces which are not Rn and Rm. You can have linear maps between them. But they are also matrices, of course, because every n-dimensional space is ultimately Rm because of that representation through the bases and those scalars becoming coordinates. But sometimes it is better to have a general viewpoint, and that can be specialized to the matrix case. So in mathematics, it's always not easy to say which is better, going from the general to the particular or from particular to the general. Some situations going from particular examples to general things is easy, and some examples going from general cases to particular things is general cases to particular things is easy. In some cases, going from particular things to general situations are easy to understand. So it's very difficult to say which is easy and which is not. So given a matrix of size m cross n, which as you know can be viewed as a linear operator from Rn to Rm, then we define the following subspaces. One subspace would be defined in Rn and another would be defined in Rm. In Rn, which is the domain space of the function A, the linear operator A, the important space is the kernel of A, set of all x element of Rn such that Ax equal to 0. This kernel has a very important implication. As we will go later on, we will see what is the implication of the kernel. It has got to say a lot about the nature of the mapping A. Then, given any map, any function, you know there is something called the image of a function. So if there is a x, then A of x is the image of the x in Rn, is the image of A under the operation A operating on x. Ax, this vector, is the image of x in Rm. So Ax, so image of A is a collection of all such Ax's. Basically, given any input, I collect all the outputs. Every output is called an image of the input in the mathematical lingo. And then the collection of all such inputs for all possible given the all possible output, that is all elements in Rn, there is a set of inputs, right? So those given those inputs, all elements in Rn, there is a set of outputs, A of x. So all these A of x is collected in a set and we call it the image set of A. This kernel of A turns out to be a subspace in Rn. And I will not wait and try to prove that these are subspaces, because this is what you should be able to prove by now. And the image of A forms a subspace in Rn. The interesting thing is that if I add the dimension of the kernel of A and the image of A, that will give me the dimension of Rn, that is n. It looks very strange because you are adding up dimension of the image space, which is a subspace of some other space, and then kernel, which is a subspace in the given space, to give the dimension of the given space. So it is basically a kind of a split that you are making. The dimension of Rn, which is n, can be decomposed into the dimension of two spaces, these two spaces. And you might ask questions that what is the real use of that? The real use of that will not be apparent even if you learn this chapter. It will be apparent when you will start actually applying them somewhere. And this may not be so useful to economics people, but I think it's worthwhile because you are learning some linear algebra. It's worthwhile to know this result because you do not know where you will use it. Even in the domain of eigenvalues and eigenvectors, which is very important for economic students, and solving, say, linear system of linear equation, this idea of rank plus nullity is the dimension of the original space, the domain space, that can come up in a sudden and unexpected ways. So any vector B is said to be in the image of A. If any vector B in Rm is said to be in the image of A, if I can find x such that A in Rn such that A of x equal to B. Essentially, to know whether a given B in Rm is an image of some x in Rn, we have to solve this system of simultaneous linear equation. Because if the matrix is represented as Aij, then this whole compact expression can be opened up into these m simultaneous equations. So our next chapter or next few lectures would be based on the Gaussian elimination method for actually solving these simultaneous linear equations. Simultaneous linear equations are hugely important in economics. There are a lot of places where, and I'll give you some references where you can go and find where simultaneous linear equations appear in economics. So I'll not deal too much with economic applications as such, because the goal is to teach you the math, the tool, so that you can go and understand what is there to apply in economics. But maybe 1 or 2 examples will come. Maybe we'll have a whenever possible we will give an example. So from economics. Now you can understand what is image of A. Image of A, if you look at it, is in some sense, or is not in some sense, that's a very wrong way to say it, is exactly equal to the column space of the matrix A. So if you take the matrix A, m cross n, and if A1, A2, An, these are the n columns of the matrix, then the image of A of x, is nothing but consisting of all possible linear combinations of these vectors A1, A2, An, which means that the image of A is nothing but the span of A1, A2, An. So this is important. So the dimension of the image of A is what? Number of so what is the dimension of the image of A? Because now it is just a column space of A. Is the number of independent columns of A. So the column space is spanned by some vectors. Among them, so these are span. So what we have learned in the previous chapters, any spanning set can be reduced to a basis. So and any independent and that reduced set also spans the original set. So just that, so the number of linearly independent columns of n, columns of A, not n, sorry, columns of A, the matrix A here. So there is an error. is the number of linearly independent columns of A, they will constitute the basis of the image of A. So the dimension of the image of A is the number of linearly independent columns of A. Since the number of independent columns of A is the rank of A, we have dimension of the image of A is equal to the rank of A. That from here where the rank nullity business is coming, and that is less than equal to mean of M and N. What is the image of A transpose? So I suppose just for heck of it I ask it. What kind of space is this? Note that the columns of A transpose are nothing but the rows of A. So the image space of A transpose are the linear combination of the rows of A, and that is called the row space of the matrix. Okay. So image of A transpose is written as A transpose Y, where Y is element of Rm, because the matrix is now n cross m matrix. So it can operate from take elements in Rm and go back to elements in Rn. So it is often called the adjoint map of A. And for any x in Rn and any y in Rm, this inequality is amazingly true. See, we are only talking about matrices with real entries. We are not talking at all about matrices with complex entries. This has to be kept in mind while we are working. Because what happens? What about complex matrices? That is an aside that we will not discuss here, because in this course, because that is not so much of great importance to economics, because economics deals with data. All the data that you will see has to have real entries. So let us see how to prove this fact, and again set A equal to A1 into An, which is the n column vectors of A. So now what is AXY? So what is A of X? So if X is X1, X2, Xn, then A of X is the linear combination of these column vectors with respect to the components of X. That is, A of X is nothing but X1 into A1, where X is having the coordinates X1, X2, Xn, X1 into A1 plus dot dot Xn into An into Y. Now if you repeatedly apply that inner product of U plus V of W is U of W plus inner product of V of W. So it's U of W plus V of W, that's splitting. So that is distribution of the inner product over the addition of the vectors. Then this can be written as, and obviously you can take the scalars out. So x1 a1y plus dot dot xn any. So what is x1 x2 xn? So this is nothing but the inner product, right, between the vectors x1 x2 xn written in the row form, and this is the matrix multiplication representation of the inner product. So this is the inner product of a vector whose coordinates are x1 x2 xn, which is x, along and with a vector whose components are, first component is inner product of a1 with y, second component is inner product of a2 with y, and the nth component is inner product of an with y. So which is, so in written in the matrix form, this inner product is written like this. This simply means, what is a1y, what is any? Basically this is nothing but A transpose Y. In A transpose Y, the columns actually becomes rows, and you know that when I multiply a matrix A with X, this can be written as that gives me a vector whose first component is the row into the vector, row into the vector, row 1 into the vector x dot product, row 2 into the vector x dot product, and row n dot product the vector x. So similarly, so a1, a2, an must be the rows of some matrix with which the vector y is multiplied, on which the vector so a1, a2, an are the rows of a vector which is operating on y. So what is that vector whose rows are a1, a2, an? That is A transpose. So x is equal to A transpose y. So we introduce here something slightly interesting geometrically. It has some implications which we will not give, because this week you are also going to get, based on what we have studied, a list of practice problems, so that you are going to receive tomorrow morning, right? Tomorrow morning or tomorrow afternoon. So before that, let us finish what we are going to discuss here. Orthogonal subspaces. So this is the definition I am giving from the book of Strang 2020, Linear Algebra for All. I forgot to mention it in the sources, but I had already mentioned before that this is this famous Linear Algebra for Everyone, which Professor Gilbert Strang has written in 2020. I'll soon have a review of that book in my YouTube channel. So two spaces V and W are orthogonal to each other if you take any V from V and any W from W, and then V and W, the inner product should be equal to 0. Means every V of the vector space V or subspace V, whatever, the vector space V is orthogonal to every element of the vector space of W. It's like a x-axis, y-axis situation. Any vector in the x-axis, that is of the form x0 in R2, and any vector of the form 0y, which is on the y-axis. If you take the inner product of these two vectors, x0 inner product 0y, you will get the answer 0. So any vector in the x-axis and any vector in the y-axis taken as vectors in R2 are orthogonal to each other. So basically the x-axis and y-axis, if x-axis is V and y-axis is W in R2, so those are orthogonal spaces. Now let us look at some important orthogonal spaces, and here comes the first starting. Kernel of A and image of A transpose are orthogonal subspaces of. So image of A transpose is in Rn, because A transpose carries elements from Rm to Rn. Please remember that. While A does the opposite, it carries from Rn to Rm. A transpose takes from Rm to Rn. Right. So kernel of A and image of A transpose are orthogonal subspaces. So how do we prove this fact? So you take any element of the image of A transpose, so and that is of the form A transpose Y for any Y in Rn. For any Y in Rm, A transpose Y is an element of the image of A transpose. And now you take any X in the kernel of A. So let us see what is this inner product, X A transpose Y. And that, you know, what we have just proved is equal to Ax inner product of Y. But Ax, because X is in kernel of A, Ax is equal to the 0 vector. So 0 inner product Y is 0. Please understand, for example, I am telling that, okay, what is the kernel of A? I am defining kernel of a set of all X element of Rn such that Ax equal to 0. Please observe that though I do not mention it, this 0 actually means the vector 0, the 0 of Rm, because A takes an element in Rn to Rm. I am not talking about the number 0, because A of X, unless it is, if X is just one number and A is just one number, it is, or A is just a kind of a vector, a kind of a matrix which is having only one column and say n rows, one row and n columns, one cross n matrix, it won't give me a number. So in general, when I am talking about Ax equal to 0, I actually meaning that 0 here is the 0 vector of Rm. This has to be kept in mind. I have not been telling them explicitly, but assuming that you understand by now. For those who are following these lectures, they should be able to gauge by now what is being said. Because if you want to be always be very critical, very careful, very rigorous at every step, that takes away the charm. So let's enjoy the charm that mathematics provides us. If we are getting always mentioning each and every nitty-gritty detail, then it doesn't leave anything to the reader's imagination. Nobody thinks, and as a result of which I am now essentially, I was giving this talk, and when I said, okay, because it's a kernel, Ax must be equal to the 0 vector, then I realized that possibly I have not spoken about Ax being equal to the 0 vector, where 0 is a vector in Rm. So here y is also in Rm, so this inner product is meaningful and that is equal to 0. Similarly, kernel of A transpose, which you can now define as of set of all y such that A transpose y equal to 0, and image of A are orthogonal. So I have just done the proof in the same way. You don't have to really look into it. So Strang divides these four subspaces into two groups. Kernel of A with image of A transpose because they are orthogonal. So this orthogonality of these two spaces have brought them into one thing. And image of A and kernel of A transpose is brought into another space. So these are called four fundamental subspaces associated with a linear map or a matrix, whatever you want to say. Rather a linear map. So, of course, you can say, what do you mean by transpose of a normal linear map, not any arbitrary linear map? That is something which we will not discuss here, but I would keep it open to you to imagine if I have just T, what is there if T is a linear map from say U to V to W. So what is the meaning of T transpose? Is there any meaning of this? Right? Because in Rn and Rm you can talk about inner product, but in general some space, linear space which may be finite dimensional, it's very important to know whether we can speak about linear products, and then only the idea of T transpose makes sense. Transpose of a linear operator makes sense. So that we will not speak here. Maybe when we have a discussion in the class, maybe tomorrow, in the contact hours, then we will actually have a discussion as to what it means. So this is something slightly crucial, but it's very important to understand that those structures. Right? So Strang called them the four subspaces. Now, okay, image of A, you can know the dimension. Image of A transpose is also the number of linear independent rows of a matrix. That will give you the image of A transpose. But the number of linearly independent columns equals the number of independent rows of the matrix. That we have already discussed previously. So image of A and image of A transpose must be the same. But the question is, what is the dimension of the kernel of A or kernel of A transpose? What is the dimension of that? Is kernel of A and kernel of A transpose having the same dimension? That's the question. Okay, in fact, they do not have the same dimension, right? So let us see. Now, this question is not always very clearly dealt in linear algebra textbooks. Some people use row reduced echelon forms and all those things. I will not get into row reduced echelon forms, not because that I won't be able to tell you what it is, or my own understanding is very poor of what it means of row reduced echelon form. We will essentially use row reduced echelon form from the next class, but I'll not specifically say how to get a row reduced echelon form, because as a young undergraduate student, I hated this idea. I don't say that this is not a useful idea. I hated this idea in the sense that I found it was so boring to do those row operations. Because you are not told how actually simple it is to do those row operations. And there are simple matrices which can be used, which are called elementary matrices, which will carry out those row operations very simply to get you to that form. So I think there's somewhere down the line there are issues about the teaching of linear algebra, about how to make the things look simpler to the students. My attempt at this is to tell you to look at everything through the viewpoint of linear combination. Keeping just that view in place, I am trying to largely convey the subject. every subject still has a lot of scope to be explained in a better way. Actually, when you start thinking about explaining in a better way, you as a teacher would also start developing a better perception of linear algebra. Every time I read linear algebra and think of explaining it, I myself develop a better perspective. Even though these terms have been known, I've been using them, it's just, but then you start looking at them from a completely different perspective and have a much better feel. So image of A, as you know, has a name now, rank of A. So that's what it is. The dimension of the kernel of A is called the nullity of A. Now, how do you find that nullity of A? What is the value? This is where the rank-nullity theorem comes into play. Because finding the rank of one must say, oh, if there are n columns of a matrix, and if there are linearly independent rows and R is strictly less than n, then maybe those n minus R rows, what about them? Those n minus R columns, will they span the kernel of A? The answer is no, because every column vector in A, in a m cross n matrix, are actually elements in Rm. But elements of kernel of A are elements in Rn. So just the remaining part cannot span anything in Rn. And first of all, those parts are linearly dependent. That is why we have thrown out. So how do you actually construct a basis for kernel of A? That is slightly hard work, and I think that is a thing that we do not talk about in detail. But here in this particular course, I do not see any methodological necessity that has to be specifically taught. But we might discuss it in the discussion hours about how such things occur. As I have written, this is a difficult task, and it needs ideas which may not be greatly benefit the economist. However, the answer to this question, what is the dimension of the kernel of A? What is the meaning on that, which you call nullity? So what is the nullity of A? That can be resolved by looking at a more general setting of a linear map T carrying the vector space V to the vector space W, where V and W are, for all purposes, finite dimensional spaces. So how do you define kernel of the matrix T and image of the kernel of the linear operator T and image of the linear operator T? This is a simple thing, just replace A in the previous definitions with T. So you see, this is the meaning of kernel of T, which is a subspace of V, and an image of T, which is also a subspace of W, because the mapping T is from V to W. It doesn't say whether V is Rn, V is Rm, nothing. We just talking about finite dimensional spaces. The rank nullity theorem, we shouldn't call it the rank. I've given this equation as the name Rn just to say rank nullity, but we cannot call them rank nullity theorem because the kernel of T is not, the dimension of the kernel of T is not called nullity. It's actually the dimension of the matrix A here, or dimension of kernel of matrix is called nullity, and the dimension of the image of a matrix is called the rank. So, but still, keeping in view that situation, we are calling this general system the rank nullity theorem. So look at that interesting result, which says that the dimension of V is equal to the dimension of kernel of T plus dimension of image of T. You might be wondering, oh, he's a mathematician, and immediately we'll start proving it. Come on, let's just close our eyes, just forget this video. But hang on, my idea, as I told you, not to just bring in a proof in front of you. My idea is to first see what kind of interesting things we can land up to once this result is assumed to be true. And then at the end, we need to really see that, okay, we have got such wondrous conclusions. Then, if assuming that Rn, this rank nullity result is true, we need to then demonstrate the rank nullity result is indeed true, because the results are so good that we wouldn't like to part with them. We wouldn't like to say that no, actually they are false. So before moving on, we discussed several important facts, right? A mapping T from V to W is called surjective if you, which means you take any element in the codomain W, then there is a corresponding U in V such that T of U equal to Y. That is called the surjective thing, that the image of T is exactly equal to W. And we call a map into or injective if whenever T V1 is equal to T V2, V1 must be equal to V2. It is not that V1 and V2 are two different elements and they map to the same element, say W in W. It can happen. For example, if you take fx equal to x square minus 2 and plus 2, both maps to the number 4 under the mapping fx equal to x square. So that is not an injective mapping. But we would be happy to have an injective map, injective linear map that works pretty well in many situations, and many of the maps are actually injective. So once I have these two definitions, then I can progress. You can say, okay, in the beginning you said, okay, we will keep our discussion to just the linear or the matrix. We can do that, but then one has to come and do these kind of calculations, and those calculations wouldn't give you any insight as to what you're doing. So that insight is best brought upon by looking at the more general scenario. Here is an example where you asked a question in a very particular setting of the matrix, but in order to answer that question, we are going back to the more general scenario. And this is what happens in many cases in mathematics. You can say, okay, possibly you want to avoid the row reduced echelon calculation, and so you are taking the recourse to this general form which we are comfortable with. Okay, that's pretty okay to think about me that, okay, he possibly wants to escape this actual computation. But you will see that those kind of computations will come up right in the next discussions. But here I would try to show that the assumption of now taking a general linear map between two general finite dimensional spaces actually does a lot of good than bad. So as a result of which we will now proceed to use this general map. A mapping T is called bijective if it is both surjective and injective. That's so. Observe that I have already told, but I have not mentioned it there, so I am writing it at this place. Observe that if T is surjective, image of T is equal to W. And here comes an important fact, and that is very important. If T is a linear map, if it is injective, then it must be having the kernel of T consisting of only the zero vector in W, zero vector in means zero vector in V, not in W. So we are, what is here? T of V equal to 0, right? Find that V such that T of V equal to 0. T of 0, because T is a linear map, T of 0 is always equal to 0. T of 0 is always equal to 0 for a linear map, right? So there are many ways of proving that T of 0 is equal to 0. I leave it to you to prove it. And for example, you take any vector x minus x. So that's a vector inverse. So x minus x is 0. So t of 0 is t of x minus x is t of x plus t of minus x, because part t is linear. So t of x plus t of minus x is equal to t of x minus t of x, because the minus comes out, so that will give you 0. So there are many ways to prove it. I don't need to tell you to prove such a simple thing. So 0 would anyway be the element of the kernel, 0 in Rn. So what is telling that if that is the only possible element in the kernel, then T must be injective, and if T is injective, then kernel will have only 0 element. So we begin by proving that let T be an injective map. So if V is element of kernel of T, then T of V must be equal to 0. Thus T of V is equal to T of 0, because this 0 is in Rm and T of 0 with 0 in Rm are equal. T0 is 0 because 0 is anyway in kernel of T. So Tv is equal to T0, and by surjectivity V must be equal to 0. It's by injectivity V must be equal to 0. Now assume that kernel of T is 0. It has only one element. Now take any V1 and V2 in V such that TV1 is equal to TV2, which means T of V1 minus T of V2 is equal to 0, which means T of V1 minus V2 equal to 0, which means V1 minus V2 is in the kernel of T, but kernel of T has only one element, which is the 0 vector in V. So V1 minus V2 must be equal to 0, which means V1 equal to V2. So whenever TV1 equal to TV2, and I know that kernel of T has only the 0 element, V1 must be equal to V2, rendering the mapping T to be injective. Next is a very important and a useful map thing. Any bijective linear map between V and W tells us a very important fact about the dimensions of V and W. And that fact is that the dimensions are equal. Right? That if T is a bijective linear map between V and W, then V and W must have the same dimensions. Okay? So once that is done, let us now understand what I mean by the inverse of a map. Right? And then we will get into our discussions, the one of equal dimensions. So suppose T is a bijective map from V to W. That is, it is injective and surjective. For each V, I have a W, and for each W, each small v in capital V, I have a small w in W such that TV equal to W. And for each W there in W, small w, there is a V for which TV equal to W, right? So which means that I can now look at W as the domain of a mapping where every W is mapped back to the V whose output was this small w. So every W can be now reversed. It can be taken back as the input and sent back to the original input V, which gave this output W. So it is a mapping which carries, so once I have a surjective map and an injective map, I can, or rather, which is the bijective map, I can carry an output back to its input. So the input takes, each input has only one output. Two different inputs cannot have the same output. Of course, a single input can never have more than one output, because then it is not a mapping, not a function. So, but several different inputs can have the same output. But when you don't have that, when you know that every input that you give to T has only one output in V, because there is injectiveness in output in W, which means every output now can be by some mapping brought back to its input. This coming from output back to input is called the inverse operation. And there is what is called the inverse mapping, which carries elements of W to elements of V. That is taking back the outputs back to the inputs. So if T is linear, is T inverse linear? So if T is a bijective map, then so is T inverse and is also linear. So the fact that T inverse would be bijective, I don't have to really prove for you. But let us have a look at things about the linearity. So if Y is in W, then the T inverse Y is an element of V. So basically it is some V. So T inverse Y is some V, some element V in V, such that T of V is exactly equal to Y. So T inverse, so if I operate T on T inverse Y, I'll get back Y. So I hope this is clear. Y is an element of W and the inverse map T inverse will carry Y to an element of V. I call that vector V as V. And what it does, it has taken back this output to its input V. So which means T of V is actually equal to Y. So if I operate T on T inverse Y, I'll get Y. So what is that? T of T inverse carries W to W. It carries every element of W and puts it back to the same element. The T of T inverse. So it's a composition of two mappings, which I'm sure you understand. That first I apply T inverse on Y, then I can apply T on the result, that is T inverse Y. So at which doesn't change the space. So it doesn't change the element. It maps back Y to Y. So T of T inverse is the identity mapping on the space W. That is called the identity map. TT inverse is called the identity map because TT inverse carries every W in W to W. Similarly, T inverse T is the identity map on V. You can do the same argument. So our job would now be to show that T inverse from W to V is also a linear map. Now, so for that, I will just prove the additivity condition. The scalar multiplication condition can be proved by my friends or viewers who are seeing it here, my students. For any W1, take any W1, W1, W2 in W and add them, W1 plus W2. So my job would be to show, for me at least here, to show that T inverse, always keep in mind that T is already linear. So T inverse of W1 plus W2 is equal to T inverse W1 plus T inverse W2. This is known. Sorry, this has to be proved. This is the first step in proving that T inverse is linear. Once this step is known, you can prove the scalar part easily. Observe that T of T inverse W1 plus W2 is W1 plus W2 because TT inverse, as we know, is the identity map. Okay. Now, T inverse W1 and T inverse W2 are elements in V. So here T inverse W1 plus T inverse W2 is an element in V. Now I am operating T on this. Because T is linear, I can write this as T of T inverse W1 plus T of T inverse W2, which has proved that this is equal to, because T of T inverse W1 is W1, which we know, because T of T inverse is identity map, and T of T inverse W2 is W2. So T of T inverse W1 plus T inverse W2 is W1 plus W2, which again means T of T inverse W1 plus W2. So T of T inverse W1 plus W2 is T of T inverse W1 plus W2. Because T of T inverse W1 plus W2 is W1 plus W2. Now by the injectivity of the linear map T, you see here this bijectivity comes into play. Without this bijection, T inverse won't be making sense. So T, and first the mapping would be defined T inverse because you have the surjectiveness, and the injectiveness is giving you also the linearity. apart from giving you bijectiveness of T inverse. So surjectiveness allows you to define, and surjectiveness and injectiveness of T inverse would because T is injective, you can show T inverse is also injective, and hence you can show that T inverse is bijective. Now here I have T of some quantity equal to T of another quantity. So by injectiveness of T, those two quantities are same, those two vectors are same. Because T inverse W1 plus W2 is a vector in V, and T inverse W1 plus T inverse W2 is another vector in V. So from by applying injectivity of T from here, I get T inverse of W1 plus W2 is exactly equal to T inverse W1 plus T inverse of W2, which is the additivity property of a linear map. And the second case you can prove, I leave it to the reader, proving that T inverse is a linear map. So now, once I know this, given the rank nullity result, we come to this very, very important conclusion. If T is a linear bijective map, I forgot to write linear here, but I have already mentioned linear on the top, that if T from V to W is a bijective linear map, then V and W have the same dimensions. Since T is injective, now we are proving this. If T is injective, we know already from the previous result that kernel of T must be equal to 0. So if you just have one element, 0 vector, so it has no dimension. My dimension is 0, right? It has a dimension, 0 dimension, 1 point. So, and why? Why you say that the 0 vector has 0 dimension? Because the 0 vector, because okay, it is spanning itself, but it is not linearly independent. No 0 vector will, alpha into 0 vector need not equal to 0, doesn't mean alpha has to be 0. You can take any alpha, that would be 0. So that is why when you have kernel of T is equal to just the 0 vector, the dimension of the kernel of T is 0, because there is no linearly independent set of vectors which is spanning the 0 set, this set 0. This is very important. This is a conceptual clarity. It's not that, oh, just take point as so geometrically, I just think of, it's just a one point thing, so geometrically it is nothing, but just, it's just a point. Point has no dimension. Point has no length, breadth or height. That is what Euclid has told us. It has no dimension. That's a good way of thinking. What the more rigorous, slightly rigorous way of thinking is this one. That 0 cannot be, 0 will span itself here, but it cannot be the basis, because 0 is never a linearly independent vector. Now, dimension of kernel of T is now 0. Hence, because there is no linearly independent vector spanning this set 0, dimension of kernel of T is 0. Since T is surjective, the image of T is W. So now, by the rank-nullity theorem, by the equation Rn, dimension of V is dimension of kernel of T plus dimension of image of T. So dimension of kernel of T is 0. So this is, we just forget this. So dimension of V is dimension of image of T, but dimension of image of T is W. So dimension of V is equal to dimension of W. This is very, very important. Another important result which the rank nullity theorem shows us, that if T from V to V is injective, then it is also surjective. It has to be surjective. And if it is surjective, it has to be injective. So if we assume when you have a linear map from V to V, now we are having both the image space, both the domain and the codomain to be V, right? Then when you talk about a linear map between a space V to itself, then if you assume it to be surjective, it is automatically injective. It is automatically, if it is injective, it is automatically surjective. The domain, the rank nullity theorem makes it absolutely simple. Because if it is injective, then kernel of T equal to 0. So, and hence dimension of kernel of T is 0. Further, the rank-nullity theorem shows that dimension of V is dimension of image of T. Okay. Since image of T is a subspace of V, and that subspace has dimension exactly equal to the dimension of V, then it cannot be a proper subspace of V. It has to be exactly equal to itself. Just think of R2. Take any proper subspace of V, proper R2, say the lines passing through 0 is a subspace. 0 point is a subspace itself. Can you find a two-dimensional subspace in R2 which is not equal to R2? You can't. You can find a two-dimensional, possibly a set in 2 dimensions, which doesn't look like a one-dimensional thing, like a square if you draw and fill it inside. Though you can have such sets, but you cannot find a two-dimensional subspace which is a proper subspace of R2 and has the dimension 2. No, you cannot have. And because of that fact, so because you have dimension V equal to dimension of image of T, and since image of T is a subspace of V, then it shows that image of T must be same as V, which means image of T is W, and which means so image of T is V, so V is the image of T is the whole space, whole range space, or whole codomain. So T must be surjective. The reverse we have left it to the reader. Again, an application of this result. So you'll have, okay. So basically, when you want to prove that when you take T to be surjective, you will basically prove by applying the Rn equality, the rank nullity equality, that kernel of dimension of kernel of T is 0, which means kernel of T must be just the zero vector. So that is the idea. Now from Axler we are going to give a proof that if you have a linear map between two finite dimensional spaces V and W, then dimension of V is equal to dimension of the kernel of T plus the dimension of image of T. The proof is instructive, and as a result of which we are going to do the proof. Even if you don't like it, I just show you the length, it is not much. Even if you don't like it, I'll do the proof. I know you might not, but it's interesting. We'll go step by step, and in small steps we'll prove it. So kernel of T is a subspace. Okay. Then I must be knowing there is a basis. I assume that the basis has m vectors. So, you are telling, oh, you are very clever. You are telling that kernel of T has dimension m. I said, okay, I don't know what is the dimension. It must be some m, some number. So, there must be some m linearly independent elements, vectors, which will be the basis of the kernel of T. So, we'll take that. Now, kernel of T is a subspace of V. Right. I am assuming that the kernel of T is a proper subspace of V. But I am assuming basically T is not a zero vector. If T is a zero vector, then T is a zero map, then the whole of the space V is the kernel. Right. Of course, you can do that technicality also. You can bring in that technicality also. Then you will immediately know that this m is nothing but exactly equal to the dimension of V. So dimension of kernel of T would be dimension of V. So basically dimension of the image of T would be 0. That's it. Because it will map everything to 0, right? So that will be obvious, that proof. So we don't want to do that obvious thing. So I am assuming that kernel of T is a proper subspace of V. So we can extend u1, u2, um to a basis of V, whose dimension I don't know, I assume. I know it by extending some, basically by extending u1, u2, um to the basis of V by adding some more vectors. This is the extension theorem we have learned before in the previous classes. So let the basis of V be u1, u2, um and has also vectors v1, v2, vn. So I have added n more vectors. After adding n more vectors, I have gone to get a basis of V, which means dimension of V is m plus n. So the dimension of kernel of T is already m, that we have assumed essentially by our choice of the basis. Then what we have to show that the dimension of image of T is n. Once you do that, you have proved the rank-nullity theorem. That's all. So our aim would be to show that I have a spanning set of the image of T which has only n vectors and they are linearly independent. That's it. So we will show here that T of V1 dot 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 T of V2, T of V1, T of V2 dot 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 T of Vn is a basis of the image of T. Now let me take any V in V. So the basis of V is this m plus n set. So there are scalars a1, a2, am and b1, b2, bn such that V is the linear combination, which is a unique combination, of course. a1, u1 plus dot 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 am, um plus b1, v1 plus dot 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 bn, vn. Then, of course, you can apply T on both sides, apply the laws of the linear map, and you have T of V as a1 tu1 plus am tum plus b1 tv1 plus dot 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 bn tvn. But what happens is that because u1, u2, um are basis of the kernel, basis vectors of the kernel, they are elements of the kernel space themselves, T of ui is equal to 0 from I to m. So this part actually goes to 0. There is no contribution. So T of V is b1 into T of v1 plus dot 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 bn into T of vn, and hence image of T. So T of V, for any V in V, T of V generates the whole image of T. So any element of the image space of T is actually spanned by is a linear combination of tv1 dot 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 tvn. So image of T is a span of tv1 dot 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 tvn. Our job is now simply to show that tv1 dot 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 tvn is linearly independent, which will, so image of T means the image of T is finite dimensional because it is got naturally the image of T has dimension, should have dimension n, is finite dimensional because it has finite elements spanning the image space. Of course, it will have dimension exactly n if we can prove that tv1 to tvn, this collection of vectors, is linearly independent. Now let us have scalars c1, c2, cn such that c1 tv1 plus cn tvn equal to 0. Basically, to show that these are linearly independent, I have to prove that c1 v1 plus c2 v2 plus cn vn equal to prove that is linearly independent, I have to prove that c1 equal to c2 dot 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 equal to cn equal to 0. Now again, applying the fact that T is a linear map, I can write this whole thing as T of, in brackets, c1 v1 plus cn vn equal to 0, because if you apply linear map on this vector, you will get back this vector, the one on the top here. So c1 v1 plus dot 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 cn vn, this vector now is a kernel of is in the kernel of T. You agree? Because T of this is giving you 0. Of course, it is a kind of, these vectors v1, v2, vn are of course non-zero vectors, then this, it will be otherwise not possible to have linear independence. So which means there are scalars alpha 1, alpha 2, alpha m such that c1 v1 plus c2 v2 plus cn vn is equal to alpha 1 u1 plus alpha 2 u2 plus dot dot on alpha m un, because u1, u2, um are the basis of the kernel of T, and this is in kernel of T. Now you bring this to the other side. So what you have, C1 V1 plus dot 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 Cn Vn minus alpha 1 U1 minus alpha m Un is equal to 0. But V1 V2 Vn and U1 U2 Um, they form the what? They form the basis of the space V, and hence they are linearly independent. And as a result of which, all these vectors C1, C2, Cn, alpha 1, alpha 2, alpha m, all would be 0. And hence I proved C1, C2, Cm are anyway 0, proving that TV1, TVN are linearly dependent, and voila, as the French would say, and that's it. The proof is done. So now go back to the matrix game again. So the nullity of A, if your matrix is mapping from Rn to Rm, so matrix of T is now the matrix A, the linear operator T is the matrix A, your V is Rn, and your W is Rm, right? And so the image space of A is nothing but the rank of A. So the nullity of A, which is the rank of, which is the dimension of the kernel of A, is now given by the dimension of Rn, which is dimension of V, minus the dimension of the image space of A, which is the rank of A, which is R. So nullity of A is n minus R. So exactly the vectors, the number of vectors which you throw out from the columns, those columns that you throw out from the column space of, from the basis of the column space of A, that number of column is exactly equal to the rank of the kernel space of A. It's a beautiful thing. There's a kind of a strange symmetry which I find, but it's a beautiful one. And as a result, we get this famous result that for a m cross n matrix of rank R, the nullity of A is n minus R. So that is what we actually started to find out. That was one of the main questions. So Axelar's book I have written, which you already know. Thank you very much. Have a happy day.